the coefficient of determination. First of all, the good news. The coefficient of determination is really, really easy to compute for linear regression models. All you have to do in order to calculate the coefficient of determination is take the correlation coefficient and square it. So if I have a correlation coefficient of, say, like 0.8, then the coefficient of determination is just going to be 0.8 squared. Now, if you take 0.8 and square it, that is 0.64. So that would be the coefficient of determination. So if R equals 0.8, the coefficient of determination is just the square of that. So that's easy. The coefficient of determination is going to be denoted by R squared. This is an uppercase R. It measures the proportion of total variation in the response variable that is explained by the least squares regression line. So what the coefficient of determination tells me is what proportion of the variation in the Y variable, the response variable, can be explained by the regression line. So I would denote this right here. If R equals 0.8, then the coefficient of determination, which we're going to denote R squared, but it's capital R, equals 0.64. So this would be telling me that 64% of the variation in the response variable can be explained by the regression line. So what am I talking about? Well, this is the golf data again, and I don't know what the regression line is for the golf data, but just pretend that's it. Well, if I were to take all of the X coordinates, and if I were to average them, and I'm not going to do that, but we got 1, 2, 3, 4, 5, 5, 6, 7, 8. So the average would probably be around in here. So X bar would be somewhere around in here. And if I look at the Y values, Y bar would probably be 4 below 4. It would probably be somewhere around in here. So I want to focus on that Y bar. Look at that line. Now, again, I don't know for this data. I didn't actually find Y bar, so I'm just saying it would be around 265. That doesn't matter. Just pretend whatever it is, it's that dotted line. And I'm going to consider this point right here. Look at that point right there. Now, that's when we swung the golf club 103 miles per hour, and the ball traveled like 274 yards. Now, again, pretend that Y bar is 265. That was the average distance that the ball traveled. Now, I would only expect the ball to actually travel 265 yards, if that's the average, if I'm swinging the average speed. So if the average speed, and again, I just kind of made this up, if the average speed was 101.5, and if I swing the club at a 101.5, I would expect the ball to travel 265 yards. But if I swing slower than 101.5 miles per hour, I would expect the ball to go less distance. And if I swing faster than 101.5 miles per hour, I would expect the ball to go further distance. In fact, if I swung the club 103 miles per hour, I would have expected the ball to travel around 270 yards using the regression line. So here's the idea. This point right here is varying from average. Part of that I can explain with the regression line, but part of that I can't explain. So this right here is the total variation. So that is how much this point is varying from average. This right here is explained. This is the explained variation. So I can explain partly why this isn't 265. It isn't because I swung faster than 101.5. So I can use the regression line to explain part of that variation. But this other part of the variation is unexplained. So again, what this coefficient of determination is doing is it's telling me the proportion of the variation in the response variable that can be explained. So it's giving me the proportion of the explained variation. So again, I made this up. This does not relate to the Goff problem at all. But if r equaled 0.8 in that problem, and if r squared equaled then 0.64, that would tell me that 64% of the variation in the distances that the golf ball traveled can be explained by the regression line. 64% could be explained. 36%, the remaining 36% of variation is unexplained. That's the idea. Now, the coefficient of determination is a number between 0 and 1 inclusive. It will always be a number between 0 and 1. If r squared equals 0, then that means the regression line has no explanatory value. If r squared equals 0, you cannot explain any of the variation in the response variable by using the regression line. If r squared equals 1, then 100% of the variation in the response variable can be explained by the regression line. So that would be perfect. Example, using the American Black Bears data from the previous sections, compute and interpret the coefficient of determination. So back at the end of section 4.1, we found the correlation coefficient for the Black Bears. It was 0.7039. So if I want to find the coefficient of determination, which is again going to be denoted by capital R squared, that's going to equal the 0.7039 squared. So if I take 0.7039 and square that, that is going to equal 0.495 approximately. So this is approximately 0.495. So I've computed it. Now I need to interpret it. So what does that mean? This means that about 49.5% of the variation in the response variable, which is for the bears, the weights. So about 49.5% of the variation in bear weights can be explained by the regression line. So we have this variation in the weights, and about 49.5% of that variation in the weights can be explained by the regression line. The other 50.5% of the variation in weights is unexplained. So that unexplained part could be because of other variables or something like that. It's not explained by the regression line.